In first semester calculus, we learned how to approximate a function of a single variable using its tangent line. So let's say we have a function f, and we fix a point x naught in its domain. Then the tangent line approximation is given by f of x naught plus f prime of x naught times x minus x naught. We use capital T for the tangent line. So for example, if f of 2 is 3 and f prime of 2 is 5, then the linear function that best approximates f near 2 is given by t of x equals 3, because that's f of 2 plus 5 times x minus 2. So that tangent line, if I graphed it, would look like this. What I know is that near this point 2, the function has to behave like that tangent line. I've tried to draw a couple little curves, not very well drawn, that locally look like this line. Now we're going to apply this in the context of systems of differential equations, particularly those that are nonlinear. So here's a modified predator-prey model, dx dt equals 6x times 1 minus x over 48 minus xy. dy dt equals minus 8y plus xy. In this model, x denotes the number of prey and y denotes the number of predators. Now, if there are no predators, y would be 0, and this top equation reduces to be dx dt equals 6x times 1 minus x over 48. Now that is just a standard logistic growth model with a carrying capacity of 48. On the other hand, if there are no prey, then x is 0, and the bottom equation reduces to be just dy dt equals minus 8y, which is exponential decay. And that makes sense. If there are no prey, the predators population will decay in an exponential manner. This system has three equilibria, 0, 0, 48, 0, and 8, 5, which we can obtain by setting this equation and that equation equal to 0 and solving for x. And the first two make intuitive sense. If there are no predator and prey separately, there will be none over time. If there are no predators, but there are 48 prey, that means the prey are at the environmental carrying capacity. What's not so obvious is that 8 prey, 5 predators is also in equilibrium, but you can get that by solving this system. Now we're going to denote this using vector notation. Let's suppose that y is the vector made up of little x and little y. Now capital Y depends upon t because little x and little y depend upon t. So then if we use that notation, then the system can be written compactly in the form capital Y prime equals f of capital Y, where f is a function from R2 to R2 given by the following. So capital F is a function whose two components are given by the right-hand sides of this differential equation. It's a function that maps vectors xy to vectors given by this formula, and that's why we call it a vector field. Now our goal is to find, for each equilibrium, the linear system that best approximates the above system near the equilibrium. And if we can approximate this system using a linear system near an equilibrium, we can perform our standard equilibrium analysis to classify the equilibria, maybe as a source, a sink, a spiral source, so on and so forth. Now the tool we're going to use is what's known as the Jacobian matrix. So let's say we have a vector field whose components are made up of the functions u of xy, v of xy. These are multivariable functions. So in this example up here, u would be that, and v would be that. The Jacobian matrix is a 2 by 2 matrix made up of the following. We take the partial of u with respect to x. Next to it is the partial of u with respect to y. Then we have the partial of v with respect to x, and the partial of v with respect to y. So this matrix is made up of 4 partial derivatives. The Jacobian matrix is to the vector field f what f prime of x is to f of x. The usual derivative is to a function. So it's the derivative of a vector field. So let's take a look at an example. Capital F of x is the vector field we saw on the preceding page. So in this case, u is the top component, which is that. V is the bottom component, is that. Now, if we compute the four partial derivatives, the partial of u with respect to x is 6 minus 1/4 x minus y. You can check that on your own. You might want to expand the top and take partial derivatives, but this is the partial of u with respect to x. The partial of u with respect to y is minus x, because if we take the partial with respect to y of that, we get 0. If we take the partial of that with respect to y, we get negative x. And similarly, the partial of v with respect to x is just y, and the partial of v with respect to y would be minus 8 plus x. So that means our Jacobian matrix is given by the following. We just take these four partial derivatives and substitute them in. Now, suppose we want to approximate a vector field near a point. What we're going to do is we're going to use this Jacobian matrix and perform a linear approximation that is analogous to the one we use in calculus. So that linearization is given by the following formula. L of xy, we use L for linearization, is capital F of x naught y naught plus the Jacobian times this 2 by 1 vector x minus x naught, y minus y naught. So in this case, x naught y naught would be 2, 1. What we're going to do is we're going to take 2, 1 and substitute it into this Jacobian matrix. That's going to give us a 2 by 2 matrix. So I'll have a 2 by 2 matrix times a 2 by 1 vector, which is a 2 by 1 vector. If I substitute 2, 1 into F, that's a 2 by 1 vector as well. So the linearization is in fact a vector field because the outputs are 2 by 1. And we call a function like this, where we take a vector and we add a matrix times a vector. We call that an affine transformation. So let's, as an example, calculate the formula for the linear approximation at the point 2, 1, and let's use our result to approximate capital F of 2, 1.8. Notice how 2.1.8 is fairly close to 2, 1. So if we substitute 2, 1 into our Jacobian matrix, which is above, we get this matrix, 9 halves, negative 2, 1, negative 6. If we substitute 2, 1 into our vector field, our original vector field, which is up here, we obtain 9 halves, negative 6. So our linear approximation would be 19 halves, negative 6, plus our Jacobian matrix times x minus 2, y minus 1. So what we're just simply doing is we're evaluating and using this formula right here. Now I'm going to simplify this a little bit. I'm going to multiply this matrix times that vector. I'm going to add 19 halves. And what I get is the following. And let me check that. Yes, okay, good. So you notice how the top and the bottom components of the linearization are both linear in x and linear in y. Only x to the first, y to the first, no product terms, cross product terms. Okay, so that's our linearization. Now we can use this linearization to approximate our original vector field near the point 2, 1. So let's substitute 2.1.8 into that. If we do so, if we substitute 2.1 into 0.8 into the linearization, we get 10.35 minus 4.7. Now the linearization is close to f of 2.1.8. In fact, I can calculate f of 2.1.8, which is 10.36 minus 4.72. So we can see how they're quite close to one another. So in the end, all we're really doing is we're taking the idea of the tangent line from Calculus 1 and we're applying it in the context of a vector field. Now we can visualize this as well. What I have drawn here, and I apologize for the bad color from my printer, I've actually drawn two vector fields near the point 2, 1. So here's 2, 1, and I've gone half a unit basically, or 0.5 units, something like that in each direction. I've drawn the vector field for the linearization and the original vector field, and we'll notice how that they look virtually the same on this small window. We can view this in an analogous manner. Here is a small square centered about the point 2, 1. What I'm going to do is I'm going to take the image of every point in the square under the function f and under the linearization, and I'm going to compare the two. Here is the image of that original square under the function f. Here is the image of that same square under the linearization. And on a small window, they look pretty close. Okay, a small window. Now this isn't really that small a window. Well, it sort of is, okay? The input window went 0.5 in each direction around 2, 1. And so now we see the input windows are the output windows are stretched a little bit from that. So here are the consequences. Let's take a look around an equilibrium. One of the equilibria of the vector field was at the point 8, 5, which is right here. This is the vector field for the original nonlinear system. Now, if we look at what's happening around this vector field, it's almost like we have a closed loop, which is reminiscent of the idea of a center for a linear system. Of course, we need to be careful because maybe this is actually a spiral sink or maybe it's a spiral source. It's kind of hard to tell. We don't want to be misled. But the idea is that near the equilibrium, we can use the Jacobian matrix to approximate our nonlinear system by a linear system. So, the upshot. At the equilibrium point 8, 5, our Jacobian matrix looks like this. However, at the point 8, 5, if we substitute that into the vector field, we get 0, 0 because 8, 5 is an equilibrium point. So therefore, near the equilibrium point 8, and that's a misprint, 8, 5, dy dt, which is our original nonlinear system, is well approximated by the matrix -1 minus 8, 5, 0 times y. But that's a linear system. And so we know how to do an equilibrium analysis of a linear system. At the point 8, 5, this matrix has eigenvalues of -0.5 plus or minus 6.3i. Those eigenvalues are reflective of a spiral sink. So that means that the picture we just looked at near this equilibrium, it is in fact a spiral sink locally. Now we could perform a similar analysis at other equilibria by taking the Jacobian, substituting in the equilibrium, and determining the eigenvalues of the matrix. And those eigenvalues would tell us whether we had a sink or a source, so on and so forth. So that is how we perform an equilibrium analysis for a nonlinear system using the Jacobian matrix.